I want to multiply numbers now by 3, but where I'm going modulo, not prime. Last time, we discussed what happened when you had something modulo 11, which was prime. When things are not prime, it can sometimes look quite different. Let's start with the 3, multiples of 3, mod 10. I first have to write the residue classes mod 10. These are easy. We're familiar with this. This is just the last digit of a number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the possible remainders when I divide by 10. I wanted to draw arrows for times 3, just to see what this looked like. So now let's continue and do this. 0 times 0 is 0. 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. 4 times 3 is 12. But because we're doing things mod 10, this is very easy. If I know it's 12, it ends with a 2. 5 times 3 is 15. 6 times 3 is 18. 7 times 3 is 21. 8 times 3 is 24. And 9 times 3 is 27. Okay. So now I have all of this drawn. It's again a very symmetrical picture. And what I'm interested in is how do those become, how do they break into loops, if at all? So when I look at this, what I will see is that I can break into loops where 0 is alone. Then I have 1, 3, 9. 9 goes to 7. 7 goes back to 1. Okay. The next loop, I'll say is 2, goes to 6. 6 goes to 8. 8 goes to 4, and then back to 2. And then there's a 5. And these are all the loops. Wait. This is now a good time to talk about why they are always loops. You see, it's very nice here that every single time what I have is on every number, there's 1 in and 1 out. So here's my number. There's always 1 arrow going in and 1 arrow going out. Why is that? That is the key reason why I have loops. Because if I don't have this, it might look very different. So the reason here is because, well, there's always 1 going out. That's obvious. There will always be 1 going out because that's how I'm drawing my picture. The real question is, why is there always 1 going in? That requires a proof. For this, I'm going to draw just one number, but I won't say which number it is. So let's do a proof of why always 1 arrow going in. So here's a number inside my bunch of numbers. I want to prove that there's always exactly 1. And I'll put a y. Let me start by first proving something different. I will first prove that I never have more than 1. That's not exactly this yet, but let me start by doing y never more than 1 arrow, which is going in to the same one. Okay? In order to prove it's always exactly 1, I need to have never more than 1, but I also need never 0. That would be the last part. What would it mean if I have more than 1 coming in? Well, now let's call this thing something. Maybe let's call this, we're always doing arrows, so let me call this thing z. Okay, this is a number, it's z. It's a residue class, it's a z. My arrows are multiplying by something. In this case, they were multiplying by 3. So let me leave that 3 here from now. These are all times 3 arrows, times 3 arrows. If I had two things both going into z, well, they come from somewhere. They come from b and a. So what does that mean? This is not a 9, that's an a. This is also not a 6, it's a b. But what is happening is I have 3 times a has the same remainder, mod 10 in this case, as z. Okay. I also have that 3 times b has the same remainder, z, mod 10. Remembering the words I used to explain last time, to describe last time, 3a is congruent to z mod 10. 3b is also congruent to z mod 10. Well, they're both congruent to z. If they're both congruent to z, that means that 3a and 3b are congruent to each other mod 10. Because they're congruent to the same thing. Another way to see this is you can now tell that if I have these 3 bars congruent to, I can subtract them, just like how I do algebra. So I can do the addition and subtraction on these 3 bars because it just means that the gap between them is a multiple of 10. What does this mean? 3a and 3b congruent modulo 10. I'm going to pull it into the next screen because here I want to be very careful. I know now that 3a is congruent to 3b mod 10. Let me remember what I'm trying to do here. I'm trying to show this is impossible. I want that it's not possible with different a and b. Because I'm trying to show that there's only one arrow. Well, there are not more than one arrow going to the same thing. Let me remember what this means. This means that the difference, 3a minus 3b, is a multiple of 10. Okay, that's what that means. Now we start to use primes, common factors. If I have this, I can even write it in the notation just to give some practice with the notation. Notation is not important for this understanding, but I'm going to write it so you're familiar with it. 3a minus 3b. These two are the same sentence. Okay? If that's the case, let's factorize. I have 3a minus 3b. I'm talking about multiples. Whenever my whole problem is about multiples, I should factorize whenever I can. So what that means is that 3 times a minus b is a multiple of 10. In the other notation, 10 divides 3 times a minus b. Aha. If that's true, now we use a very useful fact. 10 and 3 do not have any common factors. 3 and 10 have no common prime factors. There's an English word for this. What we say is that 3 and 10 are relatively prime. Let me introduce to you another English word that you will see in some of the books. Sometimes they are written as co-prime. I'm just showing you these words because I hope that these talks will get you interested in number theory, and you might want to find as many books or lessons as you can. So it's good to understand which words are which. But now, because 3 and 10 have no common factors, how can 3 times this be a multiple of 10? The only way for that to be is that a minus b is a multiple of 10. because the 3 doesn't help. I need to make multiple of 10. 3 is not going to help me. It's a different prime. So that means that 10 divides a minus b. I wrote all of this blue because if you wanted to write this with fewer words, you could say 10 divides 3a minus 3b implies 10 divides 3 times this implies 10 divides a minus b. You may be familiar with writing your work this way. Okay? Oh, how can this be? 10 divides a minus b. But what are a and b? A and b are from here. Can I find 2 of them so that if I subtract them, it's a multiple of 10? No, because if I look at these, if I subtract them, if I take the bigger minus the smaller, the biggest difference is 9. This is the largest difference. And it's less than 10 because there are 10 things in my circle. And so the biggest difference I can have is 9. So now when I look at what I have here, I have 10 divides a minus b. That's impossible. That's only possible if a and b are the same. But I said they are different. So this is a contradiction. There are different ways people write contradiction. Some people write this. That's a symbol that you can use. You may also see in some other books different kinds of symbols. I write this one because it just is easier to write, but it looks the same. Okay? So we have now reached a contradiction. What that means is, let me remember what we were trying to do. We never have more than 1 going into the same place. We still need to show that there is always at least 1. There cannot be 0. For that, let's remember how the arrows look. I have here all of these arrows. I have 10 numbers, and each number puts 1 arrow out. I have here 10 residue classes, residues. Each makes 1 arrow. Each makes 1 arrow going out. Okay, then how many arrows are there? I have 10 arrows in this picture. But I also know that each can receive only less than or equal to 1. So nobody receives more than 1. Receive meaning going into you. Well, if I have 10 arrows going out, 10 residue classes catching them, but nobody receives more than 1, that means that every residue receives exactly 1. So this implies every residue receives exactly 1. And that's why, if I look at what happens when I multiply by 3 modulo 10, I will get a picture. It will have some loops. The loops will not be as nice as the previous one. These loops now, it's not just one big loop. I have a lot of little ones. But this is why they are loops. And the interesting thing of this example is that 10 is not even prime. 10 here is not prime. But the important fact was that 3 and 10 were relatively prime. Since 3 and 10 are relatively prime, I still have everything becoming these very nice loops. What happens if they're not relatively prime? Well, we'll have to see the next bit.